Hello, my name is Soo-Hong John. I'm the 10th grade and I go to Horace Mann School, and this is my science research project. Delivering intraoral ointments using microscopic double water droplets, the capillary phenomena and surfactants. This is my background and reasoning behind research. Whenever I was tired, I suffered from stomatitis, and I essentially developed mouth ulcers. I needed to apply ointment inside my mouth, and I found it very annoying because the ointment was mixed with the saliva and I had to apply it frequently, which required more medication than necessary. Ointment is essentially an oil because it is composed of 80 to 90% oil and 10 to 20% water. On the other hand, saliva is 99% water. Because saliva is naturally formed in our mouth, ointments are frequently washed out by the saliva. Therefore, moving on to my next slide, I developed a new DDS, drug delivery system. I manufactured a microfluidic device using a glass capillary that can implement a co-flowing system that does not require separate surface modification to form double droplets designed to attach drugs to oral skin tissue or the mouth. Essentially, I intended to create an intraoral ointment that is well attached to the surface of the mouth, essentially increasing its adhesion rate, and therefore it is less absorbed by the water and therefore increases the effect of the ointment. Our initial hypothesis was that double emulsion droplets can be made when microfluidic devices are created using capillaries with different diameters. And through the research, I further discovered that the diameter of the emulsion can be made to the desired size by controlling the volume flow rate of the fluid using surfactant and shear stress in the self-made device, which I'll talk about later. And that, secondly, it is effective when administered to the inside of the oral cavity using the developed droplets. This is my experimental design. Initially, there's an ointment problem, which I talked about, that is very uncomfortable and has a short-lasting effect due to the saliva. And then through double emulsion as a carrier, I developed a new DDS, a drug delivery system, and that there's a weight loss for the ointment and long-lasting effect, and therefore an increased adhesion rate. The hypothetical diagram here represents the procedure taken to create the double emulsion droplets, which I'll explain in the upcoming slides. Keep in mind the three fluids: inner fluid, intermediate fluid, and external fluid in the microfluidic capillary device. The key points of my research. Among microfluidic systems based on water droplets can produce double and multiple droplets, as well as single droplets of low size dispersion. This can be further used to make high quality chemical products. Secondly, micro-unit emulsion can significantly increase skin absorption because of the surfactants from the composition. And confirming the first step, we created a system through simple chemical reactions that can produce uniform simple droplets and double emulsion through a glass capillary device. Our first experiment was manufacturing the capillary. In manufacturing the capillary, I essentially took 3 syringes full of the 3 fluids, as shown in the hypothetical diagram before, and put the connecting tubes inside the water. The double droplets are marked using food coloring, as you can see in the bottom 3 slides. When all 3 syringes are momentarily pressed, instant pressure is exerted, and double emulsion essentially occurs. Double emulsion, water and oil in water in this case, means that a single substance exists as a retaining droplet containing small droplets of water. The connecting tubes are very small to increase pressure, and the chemical reaction at this time follows the 2 mechanisms. 1, it allows the fusion of small fatty membranes to separate internal and external droplets. And 2, the chemical passing through or diffusing the oil-based surface without membrane destruction. Essentially, water and oil in water forcefully combine, or rather, water envelops the capsule where oil, or in this case, the ointment, is enveloped inside. A way to think about this is that the surfaces of the water and oil stacking up on top of each other. This is a further extension of experiment 1, and in this case, I used machinery, as you can see in the bottom slides, connecting the syringes in order to determine the optimal condition, combination, and ratio of the hydrophilic and hydrophobic solutions for the most amount of double water droplets formed, and I'll talk about the results in the upcoming slides. Experiment 2, I employed the different ointments that we created through the capillary on a pig's mouth. After running water that essentially played the role of saliva in the human's mouth to the pig's mouth, I measured the mass of the water that flowed through the mouth and calculated the difference in mass. Obviously, in determining the optimal combination, the lower the difference between the initial and final mass of the water, the more optimal the combination was, because that meant less ointment was absorbed and was thus more well attached and an increased adhesion rate. This was also for the extension in that I applied the ointment on the pig's skin instead of the mouth. I essentially followed the same procedure, but this time I compared the differences of the ointment adhesion rate in different environments of solutions, such as varying temperature, salinity, and pH levels. And finally, the results. Through experiment 1, we realized that Using the value of the concentration of the solutions forming double droplets, the size and number of water droplets formed by changing the internal medium external fluids were further measured, and the number of double water droplets was confirmed by checking the types of chemicals that showed the highest reaction. The largest number of droplets, which is quite interesting, the 12 and plus minus 3 micrometers of meaningful size, was made in a distilled water distilled water structure, and 15 droplets were made, as you can see in this slide in this chart here. This chart represents the number of droplets formed for these 6 solutions. And for number 5, DW, hexa, DW, and that DW represents distilled water, hexa, hexadecane, and DW, distilled water. 15 droplets, which are the most droplets, were formed. And you can also see the other substances and other solutions compared, such as ethanol here and methanol. And going back to the previous slide. Thirdly, the experiment result value, which is quite interesting and noticeable of the third experiment, ethanol span ethanol, as you've seen before, was lower than other values. When the internal and external fluids were ethanol, it was thought that the membrane of the resulting droplets burst due to the difference in surface tension. In experiment 2/3, there was a clear pH difference between the control group and the experimental group. The control group being an already existing ointment that, in the world called Oralmedi, and the experimental group being the ointment we created through the Capillary. After applying solution with an acidic component, the pH value changed, which proved our initial hypothesis. And for the mass change, 4.1 milligrams was not removed, and therefore the hypothesis of adhesion to the skin was thought to be meaningful, because that meant that adhesion rate had increased, and because the 4.1 milligrams was not removed, there was a weight loss of the ointment. Given temperature and salinity, there was a difference in mass in every experiment, and when the temperature of the water was high, the surface of the skin became soft and the absorption of ointment occurred well at low temperatures. The experimental group, made of double droplets in this case though, showed good effects at high temperatures, which is optimal for humans because the temperature inside the mouth is better at 28 degrees than 4 degrees. There was a lot of loss at high salinity. It is judged that the highest of the salinity of water, the more difficult it was to attach ointment to the skin due to sodium ions acting on the skin. Finally, the conclusion. It was possible to develop through this research a new carrier delivering drugs by double droplets through double emulsion combinations and ratios. We improved the drug delivery efficiency in the oral cavity with the manufacturing drug carrier, and I ultimately created a micelle, as you can see below, which is an image of a micelle, formed of a hybrid polymer produced using an amphiphilic hybrid polymer composed of N-hexadecane and PVA, or other substances and other oils like ethanol and methanol, as an effective drug carrier. And the image below is a micelle and that a hydrophobic head and a hydrophobic tail. And the image I talked about before, where the water envelopes the oil and that the ointment itself is enveloped inside the micelle. Thank you for listening to my presentation, and I hope you enjoyed.